In this video, let's go ahead and tackle this problem. It's question 2, it's worth 15 points. It's a transfer function given by y of s over r of s. So this is output over input equals 3s plus 6 over s squared plus 2s plus 5. We're given r of t is equal to the delta function, and we want to find y of t, the output in the time domain. So all we need to do to get the output in the s domain is multiply by the input in the s domain. So first let's transform this input r of t equals delta t into the Laplace domain. So that's going to be equal to 1. That's kind of a nice one, because if we multiply this function right here by 1, we get the same thing, and we get y of s equals 3s plus 6 over s squared plus 2s plus 5. And if we think about this, this is going to be the once we get it into the time domain, once we get y of t, this is going to be the impulse response. And if you know anything about convolution and linear time invariant systems, if we know the impulse response, we get to know a lot about the system. It's very scalable. Once we know the impulse response, we can know the response for any given input. So this is actually really useful, and this is a really cool problem. So let's take a look at how we're going to solve this. First, let's take a look at the denominator. S squared plus 2s plus 5. So that's something that's not super factorable. It has two, I want to say imaginary roots. So what we're going to do is use completing the square to get something like s plus some number squared plus another number squared. And the reason we want that is because that's like one of the forms, oh gosh. Because that's one of the forms of sine and cosine. So if we pulled up a Laplace table right here, we see that this form right here, omega over s plus a quantity squared plus omega squared, gets us, if we went in the inverse Laplace direction, we get this function in the time domain. So we want to get something in this form. So the way that we're going to handle that is using completing the square. So here we get s squared plus 2s. Half of 2s is 1, squared is 1, so plus 1. And then we have to subtract 1 too, so we're not doing anything to it. Minus 1 plus 5. Oop. Minus 1 plus 5. So this is the new denominator, and we can factor this to s plus 1 squared. And then we get this is plus 4. So this is 3s plus 6 over quantity s plus 1 squared plus 2 squared. So this is a good start. Now we have to mess around with the numerator to get the numerator in a form that's like s plus 1 plus some other constant. So what we're going to do is factor. We get 3 times s plus 2 over s plus 1 squared plus 2 squared, right? Let's break this s plus 2 into s plus 1 plus 1. So we get 3 times s plus 1 plus 3. So plus 1. We distribute this one in so we can take it out, right? And we get 3 times s plus 1 plus 3. And this whole thing is over s plus 1 quantity squared plus 2 squared. Awesome. So now we can break this fraction up into two fractions. We get 3 times s plus 1 over s plus 1 squared plus 2 squared plus 3 over s plus 1 squared plus 2 squared. So this form is easily identifiable. If we break out the 3, we get 3 times s plus 1 over s plus 1 squared plus 2 squared. This one coincides with the form s plus a over s plus a plus omega squared. So this is going to be e to the negative at cosine omega t, where omega is this number. So we get 3 e to the negative t cosine of 2t. That's the Laplace inverse of this. And then we can work with this one a little bit. What we need here is this one to be equal to omega. So what we can do is multiply by 2 over 2. So multiply by 2 over 2. So that's like multiplying by 1. We'll swap the places of these two. So we get 3 halves times 2 over s plus 1 squared plus 2 squared. And now this is a constant out front. We get 3 halves e to the negative t, and now we get sine because we're in the form of omega over omega squared. So we get sine of 2t. And these are added together. So the final answer is u of t, remember, because the Laplace transform is one-sided, multiplied by, let's take out an e to the negative t of everything. And then we get 3 cosine of 2t plus 3 halves e to the negative t sine, 3 halves sine of 2t. And this gives us an idea about the impulse response of this function. Very cool. Plotted this out. So this is the impulse response for the given transfer function. And we see some decaying oscillations as expected. So yeah, you can imagine like what happens if we throw in a really like hit the system with a hammer at the origin, and this is the response we get. So we get some pretty cool action. The physical meaning is kind of removed as we've only been given the transfer function, but we know there's some oscillations and we eventually tend towards 0. So that's pretty cool. Nice.